Engineering design is difficult, in fact extremely difficult. For any product, a customer requires a certain level of performance. So the designer needs to explore many options and complex trade-offs before finding a good solution. Take the design of a light bulb. This is described by a number of parameters. For example, its diameter, its length, the material used, and the number of coils used in the filament. Each of these can influence a performance. For example, the working life of the bulb. If we know the parameter values, we can compute the performances. For example, if we take a random set of parameter values for a bulb, we can easily compute its working life. What we really want, of course, is the reverse of this process. In other words, given a performance specification by the customer, we want to know what set of parameter values is needed. That's design, of course. Now, unfortunately, and here's the reason why engineering design is so difficult, there's no direct way of computing the parameter values needed to achieve a desired performance. However, this reverse relationship can be explored by computing the performance values for a number of bulbs.
Here at Imperial College, a multidisciplinary team has been doing research into interactive visualization. Recently, we've designed the Influence Explorer to help engineering design. This uses a mathematical model, in this case for a bulb, to compute the performances for a range of different parameter values. The data is displayed in the form of histograms, and the designer can then interact with this data to explore its internal relationships. As we can see here, the histograms display the distribution of 2 performances and 4 parameters. Each rectangle within a histogram corresponds to a single bulb. Selecting a bulb on one scale shows its corresponding values on the others. The use of lines joining a bulb on each scale allows comparisons to be made. In the early stages of design, it's useful to gain insight into the general trends within the data. By selecting a window or range on one scale, the bulbs within that range are highlighted in pink on all the other scales. By moving this range, we may discover a trade-off between 2 performances. Here, for example, between brightness and working life. Sometimes, to see general trends, it can be useful to show the mean of the selected bulbs, as shown here by the yellow circles. As well as helping to explore general trends in the data, the Influence Explorer can be used to help design a bulb to meet a customer's requirements. Upper and lower limits can be set on all the performance scales, whereupon colour coding indicates how the bulbs satisfy the requirements. Pink bulbs satisfy all the specifications, black bulbs fail 1, and dark grey fail 2 requirements. In this example, we've simulated 800 bulbs, and we can see that there are only a few pink bulbs, but there are many black bulbs lying just outside the selected ranges. So by moving the limits to accommodate these, more pink points will appear. When the designer is satisfied with the performance requirements, a set of suitable parameter values is instantly available.
But that's not the end of the design process, because in practice, things cannot be made with precision. In other words, if we're mass-producing bulbs, we cannot guarantee they'll all have the same parameter values. To overcome this problem, the designer has to work with a range of parameter values rather than a single value.
We can set up these ranges just as we did for the performances. So, for example, here we can set up a tolerance range.
The pink bulbs are still the useful bulbs. They fall within both sets of performance limits. The new blue coding indicates bulbs which fit within the parameter limits but fail the performance requirements. These are the bulbs that will fail during the manufacturing process. A simple aim for the design at this stage might be to maximize the percentage of bulbs that we found to be satisfactory when manufactured. In other words, the pink bulbs. This percentage is called the manufacturing yield. In visual terms, this means we'd like to increase the ratio of pink to blue bulbs. Thus, by narrowing these parameter ranges, we will see the yield increase from 6 to 20%.
These few examples have shown how the Influence Explorer allows the human designer to explore and thereby gain insight conducive to the design process. But that doesn't exclude the possibility of it allowing human expertise to be complemented by algorithmic procedures. Here, for example, we see the result of the computer, rather than the designer, adjusting parameter values in order to increase the manufacturing yield. The most effective way of marrying human expertise and algorithmic procedures in this manner remains to be explored and exploited. Overall, the Influence Explorer is a tool appropriate for any design problem in which performances can be computed from a knowledge of parameter values. We hope that the ideas it embodies will influence the development of computer-aided design tools.